Hi Year 9 chemists. This is the second lesson that I'm going to get you to look at for energy changes, and it's section 9.2 in your textbook. Should be around about 112, but look for section 9.2 because some of them are printed differently. This is one of those lessons where you'll notice that everything is got a red line on the left-hand side, and this is the reason why I got you to do the revision lesson from Key Stage 3, because you'll actually find that everything just suddenly jumps up and becomes very, very difficult very, very quickly. And so what you do need to do is you need to go through the lesson 1 if you've not done so already. We did cover this earlier in the year when we were at school, and we kind of left the journey at these diagrams. This is 9.1, where we started talking about energy level diagrams for endothermic and exothermic reactions, and I remember testing you on that in one of the tests. Now, in that section, there was a little clue as to what is lying in store for us, which is the energy change, and this whole thing about kilojoules of energy needed to make stuff. So that's pretty much where we are at the moment. So just a quick recap. When you have a chemical reaction, what you have to do is you have to break bonds first, and then you have to make them. So this is a simple exothermic reaction. It's a nice example. It's actually hydrogen reacting with chlorine. Very straightforward. What you have to do is you have to break these bonds, and what we do is we supply energy into the chemical reaction. So energy must be taken in by these chemicals to do this. Now, this can actually happen in sunshine, so this is quite an explosive reaction, I must say. And then what happens is, once that energy has been put in to split every single atom up, we then find that the hydrogens and the chlorine atoms would like to join to each other, and those new bonds form between those atoms. Now, these give molecules of hydrogen chloride, and that step releases energy. So the question really becomes this: do we actually supply lots and lots of energy and don't get that much energy out of it? Now, if that was the case, then the net input of energy would mean that this system would be taking in energy overall, and that would be an endothermic reaction. The other situation that we could have is we could have a little amount of energy required to break these bonds, but we get a huge amount of energy given off by these chemicals when you form the new bonds. Now, if overall you find that there is a huge release of energy, that means that you have an exothermic reaction. Now, that pretty much takes you to where you needed to get to at Key Stage 3. But at Key Stage 4, what you then need to do is you then need to be able to calculate how much energy is being given off, given a certain number of starting particles and starting material. And that's where it can kind of get hectic, okay? So a quick recap of the rule that I just gave to you, and this is really important. I'm going to test that with test you on this. If the energy taken in to break bonds is less than the energy released in making bonds, the reaction is exothermic. And if the energy taken in to break bonds is greater than the energy released in making bonds, the reaction is endothermic. This is an example of an endothermic reaction. It's actually an example of an industrial reaction. It's called the Haber process, and this makes ammonia. So making ammonia actually requires a relatively large amount of energy to break all of the bonds in this reaction. This actual reaction is the reverse reaction of synthesizing ammonia. So this is actually going backwards, okay? So let's say, for example, we have some ammonia, we've already made it, and we wanted to go backwards. We wanted to turn it back to hydrogen gas and nitrogen gas. So this step is actually an endothermic reaction. Okay, this is just information that I'm giving you. You weren't to know that before, and it's just an example, right? So ammonia, what we'd have to do is we'd have to put a huge amount of energy in order to split the hydrogens up from the nitrogens. See, hydrogen likes to be near nitrogen, okay? It actually is energetically favourable. And then what we find is if we then recombine the hydrogens together with hydrogens and nitrogens together with nitrogens, we get our products, which is 3 molecules of hydrogen here and 1 molecule of nitrogen, but that's not energetically favourable. Okay, so that step does still release energy, but it's not as much energy as we need to break all of these bonds up. Okay. Now, you might be wondering, could it just be down to the number of bonds that you break up? I mean, there's 6 bonds here, and we're only forming 4 bonds now. It could be a good rule of thumb, but the value of the NH bond is not the same as the value of the HH bonds. And the value of the HH bonds is in turn not the same as the value of the NN triple bond, okay? So we can't rely on counting bonds here. We can only get that information from tables. These tables are actually tables that are available. They'll always give you in GCSE these values. These values are called bond energies. And the bond energy is defined as the energy needed to break the bond or the energy released when these bonds form. Now that is given in kilojoules per mole. Okay, so the bond energy is the energy needed to break bonds or released when these bonds form. Now, the energy needed to make or break bonds on the list on this page over here for chlorine molecules is 242. Now, the 242 refers to a set number of chlorine particles called the mole. We have not covered the mole. We're not going to be covering the mole for a very long time. So all I need you to do is I need you to just take a real shortcut. When you actually have something in a chemical reaction like Cl2, I'm just going to skip over here. I just want you to imagine that when you have something like Cl2, the Cl2 actually contains a Cl joined to a Cl, and that bond there, for this quantity, this set quantity, is what is being referred to over here. So I have a set quantity, we're going to call it a mole, right? A set quantity, a set number of bonds that are in chlorine, and it will take 242 kilojoules to break that number, okay? The mole is kind of like a reference point for particles. You know, we can talk about a dozen eggs. We can talk about, units like a baker's dozen, which is 13. A dozen eggs is 12, okay? We know that a couple or a pair is 2, okay? So we just talk about a set number of bonds called moles, and that's all we need to think about at this stage, okay? Now, the good news is that what we can do is we can skip past this whole moles thing, and we can just look at equations, and I'm going to take you through step by step these equations, and then what I'll do is when we have the quiz, the checkpoint quiz, I'm going to ask you to work everything out and put in your own values, okay? So we've got this idea that bond energy is the energy needed to break bonds or released when these bonds form, okay? So calculating the energy changes in reaction. Now, this reaction is referring to this exothermic reaction, okay? Now, breaking bonds takes in energy, making bonds release energy. This is a situation where if the energy taken in to break bonds is less than the energy released in making bonds, the reaction is exothermic. So hopefully by these calculations, we're going to find that the energy taken in to break bonds is less than the energy released in making bonds, okay? And that will then help us classify this reaction as exothermic. Right, okay, so this is a kind of elaborate way of writing the equation. You suddenly see that there are some dashes in there, but I'm going to translate this into something that you already know. So this is, I'll just hold this like this, H2 plus Cl2 reacts to form 2HCl, right? Okay, it's skipping the whole state symbols because at this moment in time we don't really mind what the state symbols are, but we know that it's a gas here, okay? So H2 plus Cl2 reacts to form 2HCl. Now that is broken down here into H plus, so that's H2 plus Cl2 reacts to form 2HCl. Okay, that's basically translating that chemical equation, that's balance symbol equation into here. Okay, and that's all we need to know. Right, so now the reason why we need to know that is because we want to appreciate how many bonds there are that we need to deal with. So you can actually see that we've got a HH bond here. Now, if we look at our chart over here, we can get some of these numbers. All right, so the numbers we need are 436. We need 242. And we also need 2 lots of 431. 2 lots of 431 refer to the fact that we're making 2 molecules of HCl for every molecule of H2 and molecule of Cl2. Okay, so I've just put these numbers here while we were looking at the chart, and let's see how this translates. So the energy in to break each mole of bonds. Now, just again, just ignore that little bit, because the bit that I'm covering with the pen, because you don't really need to understand that just yet. I mean, you're year 9. I'm gonna break it down for you. So we got 1 lot of HH, which is 436. That's here, okay, and we got 1 lot of ClCl, and that's here. So it's really important for you to be able to figure out what bonds are actually in these molecules. And we got 2 lots over here. Okay, now those two lots are here, and that's the energy out. Remember, making bonds, which is what's happening over here with the HCl, making bonds releases energy. So this over here, if I can get this is energy in, okay, and this is energy out, all right? Now, what we need to try and figure out is this. If the energy taken in to break bonds is less than the energy released in making bonds, the reaction is exothermic. So just do a quick calculation, right? The energy in is 436 plus 242, which is 678, okay? Just so happens that, I'm just going to put the units there, okay, just for completion, right? And then the energy out is 2 times 431, which is 862. Okay, kilojoules per mole, all right? Now, then what we can do is we can figure out that the energy in, take away the energy out, is 678 minus 862, which is equal to minus 184 kilojoules, okay? So, what happens is this. The energy in, the energy that you have to put in to break all the bonds is 678. Now, that is less than the energy released in making the bonds, okay? 862. So what we do is we always go energy in, take away energy out. Now, if the energy out is larger than the energy in, we will always get a negative number, okay? A negative number. Now, that relates to our knowledge of enthalpy reactions, right? And the the energy profile diagrams, I should say. So this is kind of like a diagrammatic representation of it. What we have to do is we have to put in energy. We have to put in 678 kilojoules. That's what we calculated. It was 436 plus 242. And then what we get out is minus 862, because that was 2 lots of the HCl's that are forming. And this subtraction that we've done is basically the difference between that number there and that number there. We know that 862 is a bigger number than 678. So that's your 862, and it's downwards. It's a negative change. So on our energy profile diagram that we've started to get our heads around, the negative changes are actually arrows that are going downwards, okay? 678, that means that we climb the ladder 678 kilojoules up here. Okay, so that's your 678 minus 862. You can see that the overall change is the difference, which is 184, and it's a negative difference because what we're finding is that the energy the energy falls. The energy falls, and this extra energy is actually energy that's given out overall. So we do have to put in something. We get a huge amount more compared to what we have to put in. So overall, we actually get a decrease in energy, and that a decrease in energy in the system. The system is giving out energy, and it throws it out, and that therefore classes this as an exothermic reaction. So that is an exothermic reaction. Now, if we were to do exactly the same thing with the second example, which is over here, what we have to do is we have to figure out what the total is of all of these bonds. So that would be 6 times the value of the NH, which is 6 times 391. That gives us our energy in. That's the energy that we need in order to break all those bonds. And then the energy out that we get is what we find when this bond forms. This is called the nitrogen triple bond, and then we have to add that to 3 lots of HH. So the nitrogen triple bond is 946, and the HH bond is 436. We have to get 3 lots of that, add that to that, and that is the amount of energy that's given out in this reaction from here to here, okay? Now, all of the calculations are here, okay? To just sum that up. The energy in is 6 times breaking up all of those, okay? The energy out is 1 of those, which is that, and 3 of those, which are those, okay? So the energy in is 2346 kilojoules. The energy out is 2254. Now, is this number larger than that number? The answer is no. So the energy taken in this situation to break the bonds is greater than the energy released in making bonds. And according to this definition, that means that we would class this reaction as endothermic. That means that it's taking in more energy than it is actually giving out. So if we were to feel it, it would actually feel cold. And we can do the calculation. The reaction takes in 92 kilojoules of energy overall. And you'll notice that this is a plus sign, so plus signs mean that you actually have an endothermic reaction. Look at all of that energy that is taken in, and you don't get so much coming out. So overall, the overall change is actually this small gap over here, 92 kilojoules. Okay, so that's that one. All right. So to conclude, making and breaking bonds. Breaking bonds takes in energy, making bonds releases energy. If the energy taken in to break bonds is less than the energy released in making bonds, that reaction is exothermic. If the energy taken in to break bonds is greater than the energy released in making bonds, the reaction is endothermic. The bond energy is defined as the energy needed to break bonds or released when these bonds form. It is given in kilojoules per mole. This is a list of different bond energies representing some of the bonds that you find in molecules. We can use these values to calculate exact energy changes in reactions. These also relate to the energy profile diagrams that we have studied before. The calculation that you do is energy in minus energy out equals. That's a calculation that you have to remember. This is the energy profile diagram that's typical for endothermic reactions. This one over here is typical for exothermic reactions. Okay? Right, thank you very much for watching this. Now, it's a lot for you to take in, so there is enough for you to sort of mull over, and I'll give you a few calculations and a few questions in the quiz just to test your understanding, okay? Take care, stay safe, stay at home. Bye for now.